Okay, so yeah, so thanks for the introduction. So I think in the introduction, I was introduced with my PhD in material science. So I am mostly material scientist. That's my training as a scientist. But in the past 5 years or so, I've been going into battery technology, and I will shortly. I will get to the part that why it is all materials. Actually, I mean, in all physical engineering system that we have in our in this physical world, everything is material. So I think for those of you who are aspiring material scientists, go material scientists. Everywhere we go, we are needed. All right, and I'm sure I share this with Professor Evi Kartini as well, because we are both material scientists. All right, the title of my talk this morning is Silicon Nanostructure Anode Design. So we are talking about from 1D structure to 3D architecture. This is to enable next generation lithium-ion battery. So I am currently in Oregon Tech with Oregon Renewable Energy Center, OREC. Obviously, battery is one of our main portfolio for renewable energy anywhere in the world. The role of battery, the role of energy storage is obvious. So this particular study was done actually during the time I was in Singapore. I was with Singapore University of Technology and Design. This is in collaboration with MIT, so you will see some part of the experimental components are actually developed in MIT as well as in Berkeley lab. So there you go. I mean, you have all the logo here of the places in which I did this study.
I'm sorry, Professor Arif. I think your screen is in PowerPoint mode, not in the presentation mode.
Oh. What about now?
Okay. Yes, it's in slideshow mode.
Okay, that's great. All right, so so this work was done with my PhD students. So Sasi and Sasi Tipabotla and Ali and Ratchenko, they are my former PhD student in Singapore. Al-Obaidi is from MIT, and Tamura is from Berkeley lab. Don't worry, this looks like slide 1 of 68, but obviously I'm not gonna go through all 68 slides. I will see, and I will probably skip some of the slides depending on the time we have. So here's my agenda. I will probably talk quite a bit about the background. I think probably it's important, I think, for a battery conference such as ICBREV to know the background and the motivation of why silicon nanostructure anode. And then I'll go maybe briefly, not so much in detail, because the second part is very material science. So maybe I will just briefly mention, but this is actually a very key tool in order to study and to enable next generation silicon nanostructure anode, as well as how we form the silicon nano anode, and then what we observe and how we recommend for design of silicon nanostructure anode. So I think this community, this audience probably don't really need introduction about why we need rechargeable lithium-ion battery. I think we already know that in the past 10 years or so, you know, I mean, starting from our laptop, our iPhone, these are all rechargeable lithium-ion battery. And as far as rechargeable battery is concerned, lithium-ion is, I mean, you couldn't get any more smaller, faster ionic charge moving. And that's what it is about. The battery is about the ionic charge that can move fast, and that can be that can move fast, that can be collected fast, that can be dispersed fast. So that's what it is all about. Okay, so as I said, electron obviously from laptop to iPhone, but also electric vehicle and renewable energy. They all need high density, high capacity battery that can that only lithium-ion battery now can satisfy that need. I mean, all those things will, I mean, like electric vehicle, renewable energy, laptop, they will need slightly different profile, different characteristic of lithium-ion battery, but almost all of them will need very high energy density, especially for things that are portable. We need high energy density, can hold a lot of energy, but yet very light. Obviously, for electric vehicle, maybe not so much for renewable energy. Tesla is my favorite company. Tesla provides everything about battery, but accelerating transition to the next level of clean energy, climate change, as what we see in the video before. Okay, so I think maybe let's go a little bit basic, fundamental about talking about material science. Why lithium? I mean, this is obviously something that is very fundamental. Long time ago, lithium has been identified. If there is a battery that will be moving the fast, you know, the ionic charge will move fast, the fastest, that will be lithium. And that is simple to see, because as we can see in the periodic table of element, you will have the lightest, the smallest atom will be hydrogen. But obviously hydrogen, a lot of problems using hydrogen as an ionic charge. So then the next one will be lithium. So as you can see from the atomic number, as you can see from the atomic mass, it is the lightest, the smallest atoms or ions that can go inside any material easily because of its smallness, because of its lightness, because of its electrical property as well. So that is why lithium ion will be is basically now the most talked about, or the dominant rechargeable battery there is in the world. And as we see the current research challenges, I mean, you can see, I mean, a lot of this lithium-ion battery is all about the chemistry. It's all about, I like to say this is all about materials, whether it is the cathode or the anode or the electrolyte, they are all materials. And all battery technology, they are signified by what the material that is used in the technology. I think most of us have heard a lot about LFP, that's lithium ferrophosphate or lithium iron phosphate. Also NMC, nickel, manganese, and cobalt, and NCA. A lot of soup of alphabet soup, so that that are thrown about. They are all materials. So I think many speakers you will see in this conference will talk a lot about cathode, because I think in the last 10, 20 years, people have focused their research on cathode. Well, it's natural, because cathode is the first thing that will have to release very quickly all the ions that it holds, right? But in the future, or I think now already, soon the anode is also something that is that will determine whether or not lithium-ion battery will have high energy density. Thing about cathode is the one that release ionic charge, and anode will be the one that will receive all the lithium ions during charging. And that is equally important, because well, you have to release it fast, but you also have to absorb it fast enough so that we can create a high energy density battery. Battery is all about the ionic charge released fast, and they travel fast from cathode to anode, and they are being absorbed fast by the anode. So there you go. I mean, so what you can see here, as we are going into like higher and higher capacity and higher potential versus the current here, you will see that you will want to be for the anode, you will want it to be here, that is as high as the capacity possible, right, with maintaining like the smallest voltage there is. So we are going to talk in this session, in this keynote session, we are going to talk mostly about the anode. I will hope that this talk will be quite unique, because I think most of the research presentation that you will hear will be on the cathode side, but we will be talking on the anode side, and what are the challenges, what are the key issues, what are the solution, what are the potential solution, and how does it look like, how the next generation lithium-ion battery with silicon-based anode look like. All right, so as I said, I don't have to mention it here again, but a lot, everything is about the chemistry, everything is about the material. I think what we have here is the example here is that is an LCO cathode. Most of the research have been done in this from 1990 to 2000 to now. We have a lot of like development in cathode. I think right now our government in Indonesia, I think, have focused correctly. We have nickel, and nickel will be needed. Even though I know Tesla recently has sort of said that they can do with LFP, thus they don't need nickel. I don't think that's the full truth, because LFP is good for maybe standard range car, electric car, but NMC or NCA, in any case, if you need higher energy density, or rather in an electric vehicle application, you want to have as long range as possible. One time you charging everything, you want it to be like 500 miles. Because obviously you don't want to have what we call anxiety range. When you drive electric vehicle, unlike gas combustion engine car, we know that we will have gas station everywhere, but not so with electric charging infrastructure. So that's what we call anxiety, range anxiety. So in order for electric vehicle to have or electric vehicle driver not to have range anxiety, we have to have high energy density. And to do that, we will have to go to NMC or MCA, or rather basically nickel-based cathode. So I think we should push through with this nickel focus strategy. Sooner or later, the world will need it. We will need it, and I hope the current government maintain its emphasis on holding the nickel strategy for the future of Indonesian battery community. Okay, but I will not talk about cathode much here. I will talk mostly about the anode, which is basically this one. Right now, the dominant technology is what we call graphite. Graphite is basically nothing but carbon. So you will have carbon that is, well, in this case, it looks like a graphene, but it's not. Graphite is basically just carbon that are very porous, and because of that, it can hold lithium ion as many as possible. And because it is porous, the lithium ion can be absorbed very quickly. So that's the dominant anode materials for now. However, we know that there is limitation with carbon, and that's basically coming to the specific energy. Carbon can only hold basically about 370 ampere hour per kilogram. So this is the theoretical electronic affiliation of an anode. So whereas silicon have much higher. So as you can see here, before carbon is only 370. Silicon theoretically is 10 times. So the ability of silicon to absorb lithium ion is so much larger. So you can store more lithium ion has been done actually. Right now, what we have in terms of anode is you have mostly graphite with a little bit of additive silicon added into it, but that is not optimal. The silicon addition is already helping a lot of the energy density. So now we are thinking, why should we still have the graphite there? Because the graphite is just cheap material, yes, but it doesn't hold many lithium ion. So we want a full 100% silicon. What we have right now, I think even Tesla right now is still using mostly carbon, mostly graphite, with probably 1%, 2%, 5%, 10% silicon. So that is not optimum. We are proposing 100% silicon, and so that's the reason why we want silicon anode. But obviously, we want something. We don't always get what we want, right? Because there is always some problem. So the problem is, as you can see in this picture, silicon is able to absorb and hold lithium ions and very fast, but then as it holds and as it absorbs lithium ion, it swells. All right, and because of the expansion of its volume, mechanically there is a lot of stress, and because of that, it cracks. And that's what you see here. And this has been observed in a lot of studies. So that's the basic problem. This one is in the form of thin film. So the silicon here is basically just a thin film, like basically a planar with maybe a few micron of silicon. So what we are thinking right now, what if we don't have a film, but instead what we have, so this is kind of like a carpet, a rug, right? But what we have instead is a carpet of nano wires. So like this is what we have. The reason we want nanostructure is because, well, if it is limited volume, it can only absorb lithium ion certain amount, and it can get swollen, but not as much as it will crack. So then we control silicon to not have cracks, but yet it is silicon, and we can absorb lithium ion as fast as possible. So that's what we propose. So we have nanostructure anode, we have a nanowire of silicon, and there is an added benefit. As you can see, if you have a film here, then the surface that can receive the lithium ion is only this surface, which is this planar surface, right? But then if you have a carpet of nanowires, all this surface that is also the vertical wall of the wire, these are all open for lithium ion to come in. So lithium ion can come in, go through and go into the depth of the nanowire, and while at the same time they can absorb, they can be absorbed, they can go inside each of the nanostructure anode. So thus it will make the kinetics of the lithium ion get into the silicon anode faster. So that's a few benefits already why we want to use silicon nanostructure anode. We do still have some problem. So this nanostructure anode obviously still suffer from the fact that silicon holds a lot of ions, but then because of that, it starts to crack. And that's the reason why we want to study what is the stress evolution during this silicon nanostructure anode, silicon nanowire anode, so that we can design silicon nanowire anode that can be fracture free. And that's the reason why we get into the advanced characterization technique. So as I said, I will probably do it very fast here because this is very material science. So, but the fact here is that in the silicon nanowire, we have to study what happens in terms of stress. And what happens here in the silicon nanowire is that soon after the lithium ion come in, the lithium ion will create a core shell structure in which the core will remain crystalline, whereas the shell will become amorphous. At the same time, the core here will become more and more compressive in stress, whereas the outside here will become more and more tensile. And that's the reason why we have this tensile stress that is crack open, that is opening the crack. And that's why we see what we see in this picture. This one showing this is a core, the shell is opening up because of that stress. And this is something that we can only know if we are able to see what happens inside a silicon nanowire during an actual charging of the battery. And that is what we set out to do about 3 years ago. And we collaborated with MIT to create the experimental capability to do this. This is basically a device that is created by my PhD student. This is basically a battery. We have the cathode, we have the anode, we have the lithium, we have the electrolyte. But not only that, we also create a window here. And this is a window made of, well, this is still called glass, but it's actually Kapton. And Kapton is something that is transparent to X-ray. So that means I can use my X-ray and I can see what happens if this nanowire what happens in terms of microstructure evolution, what happens in terms of stress evolution, and see what happens during an actual operation of the battery. That is charging, let's say, in the charging cycle, what happens in the silicon nanowire here. So,
sorry, Prof, your time is 5 minutes.
okay. Okay, so that's basically what we, so we work with Berkeley and MIT to create this. This is not trivial. This is something that is a study unto itself about how to make this capability to do this experiment. But I'm happy to report here that we are finally able to see this is actually the real battery cell. What you see inside will be the silicon nanowire, and we can actually see with this synchrotron facility, we can see what happens in this silicon nanowire during charging. And this is some of the things that we've seen. But I think I probably will not have time to actually go through the microstructural evolution, but suffice it to say that with this, now we can understand how to design silicon nanostructure, 1D nanostructure, in this case, nanowire, so that the anode will not crack, but yet it is silicon, so it will have very high energy density. It will not crack. It will have all much higher surface to volume ratio. And because of that, it will be one of the potential solution for the next generation battery. But we also started this part of studying that, okay, now we know that 1D will be, 1D is already very helpful, right? Nanowire, just 1D. But what if we can make it 3D? That means we can, I mean, all this carpet will be 3D nanostructure. So we will have even more surface to volume ratio, and they will not crack because we know now how to design a silicon nano anode that will not crack, and yet it can increase the energy density 3 times. So from 1D to 3D, we increase the energy density 3 times right away, simply because we will use the space now in between this wire. We will create something like this, a 3D structure that then will increase the anode 3 times. So thus, this is something as close as possible to a bulk silicon, but yet it is not bulk. It is engineering. It is it's called engineering foam. We engineer the porosity of the method. And this is not just what we talk about or not we propose. This is something that is already been, other company in Silicon Valley have already done similar to this, not exactly the same, similar to this. So this Enovix has created something similar. They also call it 3D nanostructure anode, right? This is another, this is a method for us to create low-cost 3D nanostructure anode. So we have already shown what we can do with additive manufacturing method. So we can see here we can create a 3D nanostructure anode with low cost, because this one will be still very high cost. I don't exactly know that it is IP. It is protected intellectual property of Enovix. Unless I work in Enovix, I wouldn't know what is the technology. But I'm pretty sure it is a very expensive, capital-intensive methodology. What we have here is a low-cost additive manufacturing option. I think I will skip this because this is something similar that we have done actually on 3D different material, but that is showing the feasibility of 3D silicon anode. All right, so I think with this, I have presented what we think will be the next potential solution for anode for next generation lithium-ion battery. We propose a manufacturing solution using additive manufacturing. We've shown the feasibility proof, the feasibility evidence of the method. We created this 3D nanostructure, 3D nano architecture using copper oxide material, not yet silicon, but that's basically the next level of the next level in our study. So as a conclusion, additive manufacturing is used to enable novel 3D nanostructure anode design for next generation lithium-ion battery. So we know 3D nanostructure anode is the way, but existing fabrication methodology is way too expensive. So we propose now with electro spinning based AM. So we show that it is possible to create 3D architecture, 3D nanoscale architecture using the methodology. So I think with this, I recommend that, in the battery technology, cathode is important. Well, everything is important actually. Cathode is important, electrolyte is important, anode, this is one of the possible solution for next level of high energy density that will be needed in the next level of electric vehicle or laptop or renewable energy. With that, this is acknowledgement for my funding agencies that is in Singapore and in MIT. And I will be very happy to answer questions if there are any.